Okay, problem 4. This is a more conceptual problem, and this didn't get typeset quite well. This is saying A is less than C is less than B here, so I'll just write that in for our purposes. Less than C, less than B. Okay. So if f is continuous for all x's in the closed interval a, b, and differentiable for all x's in the open interval a, b, which of the following could be false? Okay, that's worth noting. We're looking for what is not true here. And we look at this first one. The derivative of f evaluated at c is equal to f of b minus f of a over b minus a for some c such that c is in the open interval ab. So for some x value in this interval, we're saying that the derivative is equal to the secant slope, the average slope of the overall interval. And this actually must be true. This is the mean value theorem right here. So if I have so I have 2 points, no matter what I do, so I can do some crazy stuff over here, the secant slope, this f of b minus f a over b minus a, which is right here, that slope, there has to be some point, there are actually 2 points here, I'll just pick one of them, that the tangent slope is equal to that. So right here, that's really not so great, but you can see the slopes are the same, so this is true. The integral from a to b, so part b, answer b, integral from a to b of f of x dx exists. So if f is continuous, that means that there must be some way to find this integral. I don't need to have an antiderivative, but remember that an integral is just talking about a positive or negative area between a curve and the x-axis, and if it's continuous, there is some area there, so I know that the integral must exist. F takes on every value between f of a and f of b when on the closed interval a, b, and that also is true. So if I have 2 points, I have a f of a, and I have a point b f of b here. Okay, it's a really ugly point, but you get the idea. What this is saying is f has to take on all of the values in this range. I have to hit everything in there, and that actually is true. That's the intermediate value theorem, because no matter what sort of crazy stuff I try, like if I just try to go straight over there, you can see it hits all these y values. If I try to, be sneaky and go down first, well, eventually I have to go back up, and I get there. If I try to go really quickly through this, provided that's continuous, I have to hit all of these values. So I know that C needs to be true. D, f has a minimum value on the open interval. This is the important part here, the open interval AB. So let's look back at this right here. We have a closed interval here. Let's change those to an open interval so we can see what happens. Okay, so instead of having closed points, I'll put open points, and now has a minimum value. Well, if I start going down, you can see that, okay, it hits a minimum value, and that minimum value is right here. However, if I never dip below this f of a value, and I use this open interval, if I never come back to that, you can see my limit right here. My limit is approaching, so my limit as x goes to a from the right of f of x is approaching f of a. So f of a is a lower bound of this. It's actually the greatest lower bound here. Only problem is it never actually gets there, so I don't actually get this minimum value. So this could be false. D doesn't need to be true in this case. I can approach it. Whereas if I had this closed interval, so I'm talking about a maximum value on a closed interval, that is the extreme, that comes from the extreme value theorem. So if I were to, go straight to it, you can see, okay, f of b right here is my maximum, and if I were to, go above it and then come back down, you can see I still have this maximum value. It hits a maximum that's included. So the extreme value theorem says this, but with the open intervals, it doesn't need to be true.